what we're going to do is actually remove everything back to that subdivide surface, because then we're going to, well, actually, yeah. Well, back to the deconstruct brep, but I'll show you it again because I don't think you guys followed. Okay, deconstruct brep now. Well, let me reiterate that these three components, right, a surface, divide domain squared, and subdivide surface, they're like the holy trinity for this course. Like, those three are going to almost exclusively go hand in hand anytime we need to subdivide a plane that's not exactly planar, and not exactly rectangular or square, right, or orthogonal. But outside of that, the other very, very important component that you really, really, really need to know, and this is part of that cycle I told you about yesterday, right? We construct geometry, then we deconstruct geometry, and then we reconstruct the next phase of geometry, okay? So there's nothing more, there's no more direct correlation to that particular thing than deconstruct brep, right? Because it even shares the name, right? So deconstruct brep is basically going to break it down into what it calls constituent parts. Constituent parts are the elements that are used to make up whatever geometry is there. And you can think of that as the three basic geometrical elements, which are point, line, and plane. So we've got vertices, those are your points. We have edges, those are your lines, or in this case curves. And then we have faces, which are your planes. Okay, point, line, and plane. Anytime you need to break these apart, you've got them right here in one tool. This is under the Surface tab, under the Analysis panel, Deconstruct BREP. And if you're curious, BREP stands for Boundary Representation, which is a much more accurate way of describing what Rhino calls solids, because they're not really solid, they just kind of behave like solids. Okay?
Behave, so it just looks like a solid, but it's not really solid?
Yeah, like it looks like a solid, and if you do a Boolean difference, it'll in some cases create the new surface for you, like you just cut it in half. But really, if you explode it, it's just surfaces. Yeah. So a boundary representation. All right. So with that said, I now want to take the same lessons that we applied to our class on Tuesday, and we're going to basically take that thing and we're going to put it here, right? Or Tuesday and today, really. But we're going to get the points at the intersections of the cells, and then we're going to place circles on those points, with the goal in mind of creating sort of like a warped, circular map, right? So, you have circles on the warped surface. Okay, so basically we have our vertices here, which I'm not going to get into the nuances of the fact that there are way too many than we actually need. We'll talk about that later. But we're just going to take the curve, primitive, circle, and we're going to assign these circles to each of these vertices. So I'll plug that in. And what we're going to have to do is make them a lot bigger because they're really, really small. You might not have to. It depends how big you made your surface. If you made a really small surface, yours are going to show up really big. I made a really big surface, so they're very small. So I'm going to make a slider here from 0 to 10. I'll bump it up to there. That's about right. So your circles should look kind of like that. And I know you can't really see them very well, right? They're there, but so I'm going to turn off this stuff. Actually, yeah, here's, well, okay. Yeah, let's just talk about it first. Well, yeah, let's just talk about it first. Okay, so we have the surface here, and it kind of looks okay, but on screen you're going to realize that, and it actually even shows up better up here, but see how it's darker on this edge of the circle? Right? The circle looks a little bit darker right here. That's because the circle is actually slipping underneath the surface itself, right? So if you look at it sideways, these circles are not really mapped to that surface at all. They're kind of floating around there and not really touching it properly. Okay? So that is going to be one of the greatest challenges that you encounter as a new user to Grasshopper. Okay, you need to understand that geometry has to be referentially mapped to a particular other basis point in a dynamic way. Dynamic meaning wherever that basis point gets morphed in your model by whatever process, it needs to intelligently map to it. So before I proceed onto anything more than this, do you have any questions for me about this problem? No questions. That's the question I wanted you to ask. Thank you. How do you fix that problem? Okay. The key word is your surface normals. Okay, so how many of you have heard the word or phrase surface normal? Not very many of you. Okay, a surface normal is essentially the, if you think about the relationship of the u and v domain axes being correlated to the x and y axes, then the surface normal, or n-axis, is essentially the same thing as the z-axis. Does that make sense? So wherever I have subdivisions here, or basically any point on the surface at all, it takes the average of all of the adjacent points on the surface, of course, and it finds the z-axis of that section. So if it was a flat plane, it would just be the perpendicular center of the center point or something like that. Okay, so I really quickly want to just show you a sample of what the definition looks like to find the surface normal and to map something properly, but you're going to realize that even that's not perfect in and of itself. Okay, but that one I don't want you to follow along with. I just want you to watch. Okay, so let me stop this video and then I'll do that.